Okay, let's continue. So we have been looking at this idea of frequency compensation. The goal there is to keep the closed loop system stable by doing something to the open loop system. So we started to look at the two-stage OTA, and we saw basically there are two schools of thought for frequency compensation. One is to add an LHP0 so that the closed loop poles fall on the real axis. The second is to keep the open loop poles as far apart as possible, and that was possible with Miller effect, and that gave rise to the two-stage Miller op amp. So let's refresh that. Let me just draw the two-stage OTA. So this is the first stage GM1. The conductance and parasitic capacitance at that node. Then you have the second stage GM2. So I'll call this as the GL prime, which comprises the load conductance and the output conductance. This is CL prime, which is the load capacitance plus the parasitic capacitance. So this is the two-stage OTA. As such, it will not be stable. So what do we do to make it stable? Yeah, how do you compensate it? Yeah, between these two, you put a capacitor. So I'll call this the compensation capacitor CC, right? So this is the two-stage Miller op amp. So let's write down the results that we know so far. So what is the DC gain for this fellow? Yeah, GM1 by G1 times GM2 by GL prime. And we have how many poles in the system? Yeah. So what is the low frequency pole approximately? Okay, let me first tell me the total capacitance. Here I have C1 plus CC into the DC gain for the second stage. C1 plus CC into, I'll just say it's GM2 by GL prime. What about the conductance at this node? Just G1. Again, for practical purposes, you can approximate this further as G1 by CC times this, right? Because Miller multiplied capacitor CC times GM2 by GL prime will be much larger than the parasitic capacitor C1, so we can do it. What about the high frequency pole? First, again, tell me the capacitance. Here I have CL prime in parallel with the series combination of these two capacitors. So you have CL prime plus C1 CC by C1 plus CC. And what about the total conductance here? I have GL prime. So let's write that. And you have some factor of GM2 contributing to real portion of the current. And what is that fraction of GM2? It is CC by C1 plus CC. Right? Again, the way to remember is we apply some test voltage here. You see what fraction of it appears here. It is that factor of GM2 that contributes to the real conductance. So again, So again here, if I say that my parasitic capacitance C1 is smaller than the compensation and the load capacitor, and if the load capacitor is higher than C2 at this node, then how can you further approximate P2 as? It's GM2 by CL prime, CL, right? I'm saying CC is, we'll assume that GM2 is anyways larger than GL prime. In addition, I'm saying C1 is smaller than CC, so numerator becomes GM2. Denominator, I have C1 and CC in series. C1 is much smaller, so C1 will dominate, and CL is much larger than both C1 and C2, so the denominator is roughly CL. This is under this condition, right? When the assumption is the C1 is smaller than the compensation and load capacitance, and C2 is smaller than the load capacitance. Okay, so we have two poles. Have we introduced an uninvited guest in this process? We have the RHP0. We didn't expect that. It came as a surprise. So I'll say RHP, and the 0 location is what? Today's quiz should know. What is it? GM2? by Cc. Right? So the transfer function I can write it like this: A0 into 1 minus S by the RHP 0, 1 plus S by P1 to 1 plus S by P2. So we also computed the unity loop gain frequency when we have a feedback factor of beta. And what is that roughly? What is the unity loop gain frequency? Beta times? Beta times, I mean, GM1? Yeah. Again, remember we can compute it by kind of approximating this entire thing as a first order system, because we assume that this system is well compensated. So till the unity loop gain frequency, you can approximate the transfer function as this. So we end up with a first order system. So if I have a first order system like this, what is the unity gain frequency? Yeah, I mean, beta is with, yeah, okay, fine. The unity loop gain frequency is beta times the DC gain times the pole location. So you multiply these two fellows, so you will end up with beta times GM1 by Cc. And again, just to highlight, this fellow is the unity gain frequency, right? When I say omega u, that is the unity gain frequency for this fellow alone. The unity loop gain frequency is where you have a feedback factor beta and you look at the loop gain. And okay, we also computed phase margin. I'll write it directly. So it was 90 minus tan inverse of omega u loop by the second pole minus tan inverse of omega u loop by the 0, right? So at least from the phase margin expression, it is clear that if I have to have a good stable system, that is, if I were to have a large phase margin, what can you say about the high frequency pole and the 0 in comparison to unity loop gain frequency? They should be as far apart as possible compared to the unity loop gain frequency, right? You just want a first order behavior till you reach unity loop gain frequency, and you want to keep all your high frequency poles and zeros after unity loop gain frequency, right? Because again, we know that a first order system is stable, so we try to make sure our higher order system behaves like a first order system at least till the unity loop gain frequency. Again, the example I gave is this is like the stereotypical mindset of Indian parents who try to compare their kids with the neighbor's kid and try to do all possible things to make sure their kid behaves like the neighbor's kid at least till the exam comes, right? So till the unity loop gain frequency, we want to do the same thing. Okay, so now let me sketch the magnitude and phase plot so that we get a feel. So let me I'm plotting the magnitude here. So we have a DC gain of some A0. We have the dominant pole P1, and then it drops as minus 20 dB per decade. So this is the unity loop gain frequency, which is, as we saw, okay, if I sketch the loop gain here, maybe I'll sketch the magnitude of loop gain. So beta A0. So this is approximately beta times GM1 by Cc. And after this, we have the high frequency pole and the 0. So if I look at the second pole location, I know the second pole is roughly at GM2 by Cl. The 0 is GM1 by Cc, sorry, GM2 by Cc. If I assume that the load capacitor is dominating, then which one will occur first? Pole or 0? Pole, fine. So I'll make this assumption and say the second pole occurs first. This is pole 2. So then what will happen to the slope? Minus 40. And let us say immediately the 0 also occurs. So the slope comes back to minus 20. This is kind of how the magnitude plot will look roughly. So let me try to sketch the phase of the loop gain. So I have two poles and an RHP 0. So the phase will start from what value and reach what value? 0 to minus 270. Two poles will contribute minus 180. RHP 0 will further bring the phase down. So if I sketch, let us say this is 90, 180 and 270. So we'll do something like this and do this. So if I look at the phase at the unity loop gain frequency, this is minus 180. So we hopefully will have sufficient phase margin. So system is reasonably stable. So here is where sometimes people can get confused. So let us say now I consider this situation wherein the second pole is occurring somewhere here. Okay, so which means the magnitude plot will do this. Second pole is occurring at this point, so it will start to drop as minus 40 dB per decade, and then the 0 comes. Let us say, maybe I'll draw it. Let's say this is minus 40 dB per decade, or something like this, and then the pole 0 comes, so it does this, right? This is pole 2, this is correct. So now one may say that, hey, I look at the magnitude plot, I see that this is the unity loop gain frequency now, right? So then you can say, hey, around the unity loop gain frequency, what is the slope now? It's minus 20 dB per decade. So it's a first order system. My system is stable. Is that correct? Why not? Sorry? I mean, it's a jargon, but the idea is you should look at the phase, right? So if you look at the phase, I have the second pole and 0 occurring earlier. So do you think the phase will start to drop faster or slower? It will start to drop much earlier. So if I sketch the phase, basically you might do something like this, just a rough sketch. So which means now if I look at the phase margin, the phase would have actually gone below minus 180. This will actually be unstable. Okay. So it is not possible for you to blindly only look at the magnitude plot and say, hey, it behaves like a first order system, my system is stable, right? Because significant information is present in the phase plot. Okay. You should look at both of them and make a conclusion. Right? So again, to extend the analogy of the stereotypical Indian parent mindset, this is like the parents blindly trying to force their kids to do whatever the neighbor's kid is doing without looking at the phase response, that is understanding what their kid is actually interested in, what their kid is talented in, and doing them, right? Yeah, and you thought board A plus was so simple. That's so deep insights on life. But anyways, that's a bottom line. You always look at both of these because a lot of information is actually present in the phase response. And in fact, if you just look at a first order transfer function like this, let us say A0 by 1 plus S by P1, some system. If I were to sketch the magnitude plot, maybe I'll go here. For a first order system, you know, the magnitude is doing this, Bode approximation does this. This is P1, A0. Again, this is the Bode approximation. If you sketch the actual magnitude plot, it will do this, right? And what is this drop around at P1? 3 dB, you guys know. But now let's say I sketch the phase plot. At the pole frequency, what will be the phase? This will be at minus 45. Correct? So as you see now, right, if I want to see if I have a pole or 0 in a system, generally, only looking at the magnitude plot will not give you a lot of info, because you see the magnitude has dropped only by 3 dB. Whereas you see the phase, you would have incurred significant phase drop. So which means you can get more information about whether you have poles or 0 around a particular frequency if you actually look at the phase plot than the magnitude plot. So just don't look at only the magnitude and make any conclusion. That's the bottom line. So hopefully till this point things are clear. So if you are now comfortable with two-stage Miller op amp at block level, now let's get into transistor level details. So first I have to have the first stage that takes in two inputs, amplifies the difference and gives a single-ended output. What circuit can do this? The 5 transistor OTA. So let's first sketch it. Again, we can have the 5 transistor diff amp using an NMOS input differential pair or a PMOS input differential pair. I will sketch with an NMOS input in the class, but we can take it as an exercise and try to sketch the same with a PMOS input version. So let me first sketch the 5 transistor OTA. Let me draw the output side first. So let me label the transistors also. Say this is M1, M2, M3, M4, M0, and let's say this is biased with the current I0. This is the output. So first stage is done. So yeah. Now what about the second stage? I need to take single input and amplify it and provide a single output. What is the simplest configuration, you know? Common source. So again, here I can have an NMOS common source or a PMOS common source. So basically I can have two possibilities. I can have a PMOS input as the common source, or I can follow it up here with an NMOS input as the common source. Which of the two do you think is better, or I can use either? Yeah, why not NMOS? I like NMOS more. Why not? Yeah, okay, can you explain more? You're saying you're getting higher output swing in NMOS. Why? Okay, maybe I'll do it this way, right? So let us say I look at the first stage. Both are biased at the same bias voltage, because in negative feedback the two terminals will be at the same potential. Then what can you say about this VD1? What is VD1? VDD minus VSG3 at I0 by 2 current. And what can you say about VD1 and VD2? Equal, because I have given common mode excitation. So this is also equal to VD2, right? Now let's say the second stage is used with an PMOS stage, and let's say it's biased with some current I6. What will be the required voltage here? VDD minus VSG of that PMOS transistor, let's say VSGP at a current of I6. Now if I were to use an NMOS here, biased at the same current I6, what should be the voltage here? Just VGS of that NMOS at the current of I6. So now you tell me which of the two is better. Why? I mean, you see, right, for the first stage output, yeah, the output of the first stage is at VDD minus VSG, right? And this voltage is more convenient to be used with the PMOS, correct? Naturally, the first stage here is at a voltage which is more suitable to be used for a PMOS input second stage, right? I'm not saying you cannot use NMOS, but with respect to the like biasing conditions, PMOS is much better in this case. Is that okay?
So if we use it with an NMOS, then we can size the NMOS we can make a very small NMOS, because we have a higher gate to source voltage.
Correct.
So we require.
No, you have higher gate to source voltage, which might not be great, because then your VDS has to be much greater than that to be in saturation, right? If you just don't worry about anything, right? I have a VDD minus VSG at the gate here, the same voltage can be applied here. So it's more suitable here. I'm not saying you cannot use an NMOS at all. You can use, but it might require a lot of sacrifices to be made. Is that clear? So okay, and by the way, here PMOS seems to be a better choice, because the first stage here is an NMOS input pair. If I were to have a PMOS input differential amplifier here, then an NMOS stage would be comfortable. So then let's, now it's clear. I have to have a PMOS input, so let me mark that. So I have I'll draw a PMOS common source. Let me call this M5. And of course, at the drain side, I should ideally have a current source. And how will I realize this current source here now? NMOS transistor. So let me draw that also. I'll call this M6, and you can basically mirror the current from this branch itself. Okay. So let us say this is to be biased with the current I6. You actually can size M6 and M0 appropriately so that the ratio of the currents here is what you want, right? Simple current mirror. So this is now good. So this is the two stage. Now to compensate it, what should I do? Put a capacitor across first stage or second stage? Second stage. Second stage is this fellow, the simple common source. I should put a capacitor from the input to the output of the second stage. So that is essentially this. Right. So here let's quickly figure out the positive and negative terminal. I know this is the output. How will I find which is positive and which is negative? I mean, let's assume something. I'll increase the voltage here. So what will happen to this drain voltage? Decrease. So which means the gate voltage here decreases. What will happen to the drain voltage? Increases. So if this gate voltage increases, output will. So this is inverting or non-inverting? Inverting. I mean, I'm increasing this, output is reducing. It's actually inverting. So this is the inverting terminal. Okay. So I'll erase all these things. Oops. Okay. Oops, this also went off. Okay, fine. Okay, cool. So now we'll do the same thing as we have been doing. First, let's see what is the operating point so that we know things are in saturation. Then the small signal properties. And operating point, at least for the first stage, we already know what is the deal. So if I apply the same voltage here, we know what are the two voltages at this node. No confusions. So what can you say about the output here? What is the DC potential at the output? I mean, first stage is clear, right? I don't think I need to explain further. So if let us say apply the same voltage here, what are these two voltages? What do you think is the DC potential at this node? Any guesses? Overdrave of M6. That is the minimum voltage the output can go, right? I mean, the output has a range of voltages it can go. But what I'm saying is, if I apply, let us say, two voltages, identical voltages at the gate, what do I expect to measure at the final output here? Huh?
VB minus VTH of 2 plus VTH of 5.
Why is that so?
So this is an NMOS and PMOS, right?
Correct.
The midpoint isn't defined, right?
He's saying it's not defined. I mean, if you recollect, this is a problem set I gave you in the third practice set. Let us say you have two current source like this. I mean, remember that I have a PMOS transistor whose source is fixed, gate is fixed. So it is acting like a current source. NMOS transistor is here whose gate is fixed, source is fixed. It is acting like another current source. Let us say even magically, by luck, I made sure the two currents are equal. Say it's some IX and IX. Both are equal. Then what can you say about this voltage? It's not defined. This is a problem I gave you to work. So this is not defined, right? And in practice, this is even serious because I have an NMOS and a PMOS current source like this, right? And whatever I do, it is not practical for me to make sure the two currents are equal, right? So which means, let us say I have a case where the NMOS current is greater than the PMOS current. Then what can you say about this voltage Vx? We are pulling out more and more current from this node than the current that is being pushed in. So the node potential will drop. So if this potential keeps reducing, what can you say about the NMOS transistor? It will go into triode region, right? So which means I will say NMOS enters triode. And once it enters triode, the current will increase or reduce for the NMOS transistor. reduce, right? And that's how the current for the NMOS transistor will reduce and will make sure that current equals the PMOS current. But is this a good thing or bad thing? Why? Why is it a bad thing? I mean, finally I see that this is happening, and let us say the NMOS current reduces, and finally the NMOS current becomes equal to PMOS current. So what's the problem? No, I mean, yeah, that's the simplest thing, right? I mean, output is defined. It will go to the drain voltage will reduce and reach a value so that the NMOS will be in triode and the current equals the PMOS current. But that is not something you want, because one of the transistors is going to triode. Opposite will happen if PMOS current was greater than the NMOS current. Okay. So in practice, you should never have a case where you have two independent current source connected in series like this. Okay. Should only have one of the current source to be independently biased, while the other current source has to be biased based on this guy. So there should be some feedback mechanism that goes and tunes this current so that the value of this current source is equal to the independent current source. Both of them cannot be independently biased. That's the idea. Is it clear?
Small doubt.
Yeah.
When we are figuring out the terminals, plus and minus terminals,
Right.
that first green node was it was increasing.
Let's see.
Yeah. So isn't the output is coupled? Isn't the output
Okay. Good question.
by CC?
Yeah. See, but the thing is, when you are looking at the gain, you want to look at the DC gain. Correct? So with respect to the DC gain, capacitor is not functional. This is happening. Okay. But even if the capacitor is there, the capacitor will provide some path, but you have a stronger path from this. Correct? If this potential increases, gate voltage of the PMOS increases, so the current that is being pushed in will reduce. So that will be much stronger than the additional current that CC will start to come. But the simplest thing is to look at the DC, right? You ideally want a large DC gain. So
Then why do we know capacitance as well calculating DC gain?
DC gain at DC, what can you say about the capacitors? Okay, so if this is clear, now we know that we need to have some feedback mechanism to set one of the current sources based on the other, and as such there is no feedback mechanism here, because here both of them are independently biased. But we are engineers, we should never lose hope, because finally where is this op amp being used then? In some kind of global negative feedback. So let us say this is used in some kind of feedback system like this, a simple unity feedback for example. And let us say here is where I apply the input at the non-inverting terminal. Let us say I apply a DC bias. I'll call the DC voltage to be VCM. VCM means a common mode voltage. That is the jargon we'll use for bias voltage. Okay, so this I'll start to use VCM instead of VB. The reason will be clear few weeks down the line, but let's stick to this notation that the bias voltage I'll call as a common mode voltage VCM. Just a notation. So now what can you say about the output here? That will also be approximately at VCM. So now you see that with this feedback the output bias is set. Fine. So now let's actually go and see, if I put this guy in unity feedback, this entire transistor circuit, whether one of the current source is biased dependent based on the other, because that's what we eventually want in a transistor level circuit. In a transistor level circuit, right now I have two current sources independently biased. I'm hoping that when I put it in negative feedback, one of the current source will be independently biased, while the other current source will be biased based on the other one. Let's verify that. So let me put it in unity feedback. So I have to connect the negative to the positive. This is the negative, negative to the output. This is the negative, this is the output. So I'll actually go and make a connection like this. Maybe I'll reduce the size. and this is the other terminal is the positive terminal. I'll bring it out like this so that it's clear. This is the positive terminal. Here is where I'm applying the bias voltage, the common mode voltage VCM. So now you see that, now among M5 and M6, which of them is independently biased? M6, because this gate voltage is free for you. You can connect it to anything you want. So this seems to be independently biased. Now let us see if there is some feedback mechanism that makes sure the currents in these two transistors are equal. I'll take the same case. Let's assume the current here is I5. Let me assume that the NMOS current is greater than the PMOS current as before. Right. So the current that is being pulled down is more than the current that is being pushed in. What will happen to this voltage? If I call this V out, what will happen to V out? I'm drawing more current from this node than the current that is being pushed in. V out will decrease. And remember, V out is connected to my inverting terminal. So which means the inverting terminal voltage also decreases. So let me mark it here. So this will reduce, which means the inverting terminal reduces. Then what can you say about this voltage VD1? If the gate voltage here reduces, what can you say about the drain voltage? Increases. So this will increase. Then what can you say about VD2? That will decrease. So the gate voltage of the PMOS transistor decreases. So let me mark it. So which means the gate voltage of the PMOS transistor decreases. Then what can you say about the current in M5? That will increase. Is that what you wanted? So now you see that there is a feedback mechanism, and that feedback mechanism is happening because of the global negative feedback you have around the op-amp. So this feedback is making sure the current in the PMOS transistor is biased based on the current flowing in the NMOS transistor, and this ensures that the two currents are equal. Is this clear? Okay, so now let me erase this. Cool. So now at least I know that these two currents are guaranteed to be equal. That much is clear. In that case, what can you say about this voltage if this current is equal to this current? Okay, what is the current flowing in this transistor now? I6, fine. If this transistor must carry a current I6, what can you say about the gate voltage of the PMOS transistor? Yeah, so I will say the negative feedback loop, it is setting VD2 to be what value? VDD minus VSG5 at a current of, so that is the voltage that will get set to. Now you also expect that the inverting terminal voltage will be at VCM, correct, because it's in feedback. That is the assumption we are making. So if these two are equal, what can you say about or first lead? What is VD1 then? What is this voltage? VDD minus VSG3 at what current? I0 by 2. Okay. This much is clear. Now if I assume that the inverting terminal and the non-inverting terminals are equal, and which is in turn equal to the bias voltage, the common mode VCM I have applied. If these two voltages are equal, what can you say about these two voltages? They should be equal. Okay, but let us say by design I choose VSG 5 at a current I6 to be not equal to VSG3 at a current I0 by 2. I see that VD2 depends on VDD minus VSG5. VD1 depends on VDD minus VSG3. If I choose these two VSGs to be not equal, what can you say about VD1 and VD2? They will not be equal. But if the inverting and non-inverting terminals have to be equal, then VD1 must be equal to VD2. Or I will say if VD1 is equal to VD2, the inverting and non-inverting terminals will be equal. Now in my design I have chosen it this way. So VD1 is not equal to VD2. So what can you say about the inverting and non-inverting terminals? They cannot be equal. Is that logic clear? So which means I will say the inverting terminal cannot be equal to the non-inverting terminal.
But we choose the values of
Yeah. No, we choose only for the non-inverting terminal, right? I mean, this is the circuit we have. Only the non-inverting terminal we have control. We are assuming that the negative feedback will set this also to VCM, right? But looks like if you choose the VSGs to be not equal, that will not happen. Because at the end of the day, negative feedback loop is trying to keep the currents in these two transistors to be equal. Okay, so let me repeat it, right? So negative feedback loop is trying to keep these two currents equal. So which means the drain voltage VD2 is biased and set to VDD minus VSG5. And of course VD1 is set to this value, VDD minus VSG3, right? Now if these two VSGs are not equal, then my drain voltages are not equal. We know that if the drain voltages are equal, the gate voltages are equal. The drain voltages are not equal, so the gate voltages cannot be equal. Okay. So which means now my inverting terminal will not be at VCM. It will be VCM plus some delta VOS, some offset voltage. Okay. And this offset we call as the systematic offset. So is this clear why there is a systematic offset in the circuit?
So that is only when we choose the gate source voltage to be
Not equal. Yeah.
Sir, can you modify the sizes so that they become equal?
Yeah, that's where I'm coming at. So let us say, I mean, you didn't know anything, you designed it incorrectly like this. You know that you are going to have offset. So what should be the fix to eliminate this offset? No. Yeah, that's what is the end goal? I mean, that's all correct, but that's all. That's the final thing. You want to keep these two VSGs equal. Fine. So maybe I'll write it. I don't have space, so I'll erase this. Hold on.
So if VSGs are not becoming equal, then why doesn't the OTA do an unequal distribution of current? Say, like right now you have said that the M3 branch is I0 by 2 current is flowing.
Yeah, exactly. Yeah.
A little bit less current flows, then VSGs can become equal.
No, little bit less current will flow, but the idea is the current in a transistor weakly depends on drain voltage, right?
Right. Yes.
So here the drain voltages are not equal. So the change in the currents because of this unequal drain voltage will not be so much. I mean, of course, the current will not be exactly I0 by 2, I0 by 2. But the change in the current you will observe will be much smaller compared to the change you will observe in the drain voltages. Is that clear? So that's why we don't worry about that. But again, you guys understood that if I were to eliminate this systematic offset, so let me mark it here, to avoid systematic offset, I should keep the VSG of M6 at whatever current to be equal to VSG of M3 at a current I0 by 2. Okay. Sorry, VSG of M5, right? Sorry. So again, let us say if I choose the length of M5 and M3 to be equal. Now remember, if I fix the length and one of the parameters in the lookup table, all the other parameters are frozen, correct? So if I choose the length to be equal, if I were to have the same VGS, what can you say about the other parameters, ID by W, GM by ID? They should also be same for the transistors, right? So which means I will say ID by W of M5 must be equal to ID by W of M3. Right. Basically, if you want to keep the same VGS for the same length, these two have to be equal, because the moment I fix the length and one of the lookup table parameter, everything else is kind of frozen, right? So this is the design choice you have to do. You keep the same current density for the PMOS transistors, right? So which means I should have the same current density for M3, M4 and M5, right? I'll just mark it here wherever I can mark it. So I'll say same length and ID by W. So this is a design choice you have to do while you are designing a two-stage OTA like this, to make sure that there is no systematic offset. Okay. Cool. So now, I mean, let us say even if you don't do it, I mean, let us say you don't do this, you don't keep the VGS equal, there is going to be systematic offset. You can actually compute how much the systematic offset will be. For that, let me write the drain voltages. So I know my drain voltage VD1 is VDD minus some VSG3. I will not write the current for simplicity. VD2 is set to VDD minus VSG5. Correct. Now nominally I want these two drain voltages to be equal. Correct. So I can write my VD2 as VDD minus VSG3 plus some small delta V1. Correct. Where delta V1 will be VSG3 minus VSG5. Correct. I know that VD2 is not equal to VD1, so I am writing VD2 as VD1 plus a delta V, where delta V is the difference between the gate to source voltage. So if delta V1 is a small signal, I can do small signal approximations. I know that at the output of the first stage, I have a small signal voltage delta V1. So what should be the corresponding delta V at the input then? No, at the first stage output, I have a small signal output voltage delta V1. So what should be the corresponding change delta V at the input side? Delta V? That's all. What is the gain? I mean, delta V1 should, so which means the input side offset is the first stage output delta V1 by the gain of the first stage. And what is the gain of the first stage? GM of which transistors? Yeah, let's say GM2 into RO4 parallel RO2. This is one simple way to actually go and compute. So again, as you see, if the gain is very large, the offset is going to be small. But if you actually go and use the same current densities for the PMOS transistors, you will not have this offset at all. So this is a better design choice to do. And I mean, we call this a systematic offset because in practice, we also have offsets due to random phenomenon. There will be random mismatches between the two differential halves that will result in a random offset. But that is a completely different phenomenon that is happening because of things that are not under your control. Okay? Whereas systematic offset is happening because of things that are completely under your control. And the lame analogy I give is this. So let's say you cook biryani at home. Every time you follow the same recipe, same thing you do, but due to some changes here and there, the taste might change slightly. That is like random mismatch. That's not under your control. But let us say some uninvited guest comes to your home and they insist on cooking biryani for them, and then you get pissed off. So you intentionally put lot of water, lot of rice, lot of salt, overcook it. That is like systematic offset. So that is like things which is under your control, but you intentionally do or not do something. Okay. So in general, in circuits, systematic errors are those that can be avoided if you do something. Random errors come because of things that are not under your control. That is in the foundries hands. Okay. Cool. So again, the bottom line of discussion should be this. So anytime you have a high gain op amp or an OTA like this, the bias point will be set by the global negative feedback you have around this guy. So even if it's a unity feedback, if this is at VCM, this is set to VCM. And even if you have inverting amplifier kind of configuration, something like this, here again you will connect this to some bias voltage VCM. So at the input side also, if you feed in the same bias voltage VCM, then what will be this? That will be at VCM. What will be the output? That will also be at VCM. Okay. So in general, the DC operating point or the DC bias points for a high gain op amp is set by the DC negative feedback around the op amp. So I'll say DC negative feedback sets the DC operating point. That's how we want your bias points to be set, by some kind of negative feedback, especially if you have cases like this where you have kind of two current sources. Then you should have only one of them independent, other should be dependent on this. There should be some negative feedback setting. So having DC negative feedback around op amp is very crucial, and it is because of this reason, if you actually look at this circuit, so I'm sure you guys have seen this. What is the circuit? It's an integrator. So here let us say I give the same thing. So is there a DC negative feedback around the op amp? At DC the capacitor is open, so there is no feedback at DC. So which means now you can clearly see the output operating point here will not be defined properly, right? So which means the transistors will not be in saturation, so things will not work, which means you will not get enough gain from the op amp. Okay. For this reason, you will never find an integrator used in open loop like this. It will always be part of some big system, and that will ensure that there is some global DC negative feedback like this. So there should be some kind of DC negative feedback around an op amp, and only that will ensure that the bias points are all set properly. Only then transistors inside the op amp will be in saturation. Only then you get high gain from the op amp, and op amp will behave like an op amp. Okay. So I will remark it here. So I will say DC negative feedback around the op amp, I will say it's a must. If this is not there, transistors will not be biased as you want, nothing will be in saturation, and you will not get enough gain from the op amp. Cool. So now I'll just do one last thing and we'll wrap up today. So we have now seen the DC picture. So we'll just briefly look at the small signal picture. We already know the poles and zeros here, but I'll just remark it once again and we'll wrap up. So this is the schematic implementation, and I'll copy the block level model I had somewhere. Where did the block level model go? So this is the block level model. So we have added everything. So finally at the output I should have a load resistor. So let us say you try to add a load resistor. So would you add the load resistor like this to ground? What will happen if I add this to ground? Yeah, it will start to draw current, bias point will be screwed up. So what should you change here? Huh? No, but you can, yeah, one thing is to put a large capacitor, but on chip we don't do that because capacitor takes a lot of area. What is the simpler thing? Oh, I mean, I thought we saw this before, right? Okay. Huh? Yeah, you connect this end to the same voltage, DC voltage here, right? And let us say it is all the same VCM voltage, you connect this to VCM. Right? Remember that whenever I draw a ground here, this is all small signal ground, which means in the large signal picture you connect it to some DC bias point, which could be a ground or any other DC voltage. And here you connect it to the appropriate bias voltage that is equal to this, so that it does not draw DC current, and you have the load cap. Okay, load cap can be connected to ground or anything, that doesn't matter.
Sir, if we change VCM, then we have to change the voltage there also.
Yeah, the idea is, you, let us say for your op amp, you basically have the inputs here, negative, you will have a supply, you have a ground, and let us say you also have another pin for VCM. So typically this one VCM will be connected internally to all of them, right? So you just feed one VCM externally, and that will make sure everything changes. Okay, cool. So here only one point I wanted to make. See, you guys know what is G1, C1 and all, right? G1 is the output conductance at this node. C1 is the total parasitic capacitance at this node. That you can write it is from drain to bulk of this transistor, drain to bulk of the transistor M2, gate to source of transistor M5. And typically the thing to remember is gate to source capacitance will be the dominant capacitance in any parasitics. So if I were to write, C1 will be dominated by basically CGS of M5. Okay, because everything else is connected to the drain of a transistor. The parasitic capacitance from drain is typically very small compared to the gate parasitic capacitor. And you guys know we have 2 poles and an RHP0. One addition I want to make is the following. So here the first stage we have approximated to be a first order system, but this is your first stage. In addition to this parasitic capacitor C1, is there some other pole that you will have here? For the first stage, of course you will have a pole at C1, due to C1, that is giving rise to this thing. But is there some other capacitor here that can contribute to pole here? In the first stage alone. Yeah, at VD1, remember, if you have a capacitor some C3, that will introduce another pole. And what is the pole location roughly? C3 is the capacitance. Looking in resistances, GM3. And if you also recollect, that also introduces a left half plane 0 actually at twice this frequency. Okay. So in addition to the existing 2 poles and one RHP0, you will also have a third pole and an LHP0 here. But the idea is, if you look at the second pole here, that is going to be GM2 by CL. That is from here, right? GM2 by CL. And which transistor contributes to GM2 here? Transistor name is what? Yeah, GM5, fine. Now if you compare the location of this second pole and the third pole, CL is a load capacitor that is going to be large. C3 is a parasitic capacitor here. So do you think P3 will be at a higher frequency than P2 or lower frequency than P2? So typically P3 will be at a higher frequency. So the 0 will also be at higher frequency. So usually it is okay. As long as you keep your non-dominant pole P2 to be greater than omega U loop, the other parasitic capacitors will also be guaranteed to be higher. So you are okay. But you should remember that it is not as though you just have 2 poles. We have an additional pole and an LHP0 here. So I'll stop here and we'll resume. Sorry if I exceeded time. Yeah.